Okay, so okay. So in the previous class, we learned how to implement the load use hazard. So in order to implement this load use hazard detection, actually, I mean, this is the load hazard detection unit. So the first, we need to detect the load use hazard. So that means that the former instruction is the load instruction, and then the follow instruction use the result of this load instruction. Okay, the very next instruction. And then, so in the previous class, I explained when to detect this load use hazard, and then how to detect the load use hazard, and then what's the required operations for this load use hazard. So you need to remember these vectors. So when and how, and then what is the required operation. So actually, when the load use hazard is detected, then we need to store the instructions in ID stage and instruction fetch stage, because if the load instruction is in the EX stage and then the following instruction is in the ID stage, and then if the load instruction is in the memory stage, then the following instruction need to use the result from this load instruction. But as I said, the result is not generated yet, so the result cannot be forwarded. So the instruction is in the instruction decoding stage should be stored, and then also this instruction is stored. So it's a pipelining. It's pipelining. So that means that it's the former instruction is stored in a certain stage of the pipelining, then the following instruction need to be stored. Okay, that's obvious actually. So because this is pipelining. Okay, and then because the instruction in ID stage is stored, then we need to generate bubble. So bubble means the no operation. So that means this instruction does nothing. Okay. So then we learned about the load use hazard, and then we learned how to implement hazard detection unit. Actually, this is a very important topic. So you need to understand how to implement this hazard detection unit. So in the previous class, I explained about the control hazard. So why does control hazard happen? So you need to remember. So because the result of the branch instruction, that means that the condition of the branch instruction is reserved late. Okay. So until the condition of the branch instruction is reserved, we do not know actually the next PC. So that means that the next instruction. The next instruction can be the target of the branch instruction if the condition of the branch instruction is true, or the next instruction can be the very next instruction. So that means that the instructions of PC plus 4. Okay. So if the next instruction is the instructions by PC plus 4, then we have no problem. The clock cycles are not wasted. Clock cycles are not wasted if the branch condition is false. But problem is that if the branch condition is true, then the PC should be the target of the branch instruction. But in order to update the PC as the target of the branch instruction, then this processor need to wait until the condition of the branch instruction is reserved. Okay. So Actually, so we can solve. So that means that we can solve the data hazard with data forwarding. So actually, it's the former instruction is R type instruction. Then we can solve data hazard with data forwarding. Okay, but we do not avoid data hazard if the former instruction is load instruction. Actually, the control hazard is the same. So actually, we cannot avoid control hazard. Okay, we cannot avoid, but we can reduce the wasted cycles by this control hazard. And then I also explain how we can reduce the wasted cycles by control hazard. So instead of using this ALU for the branch instruction, we can add some special hardware that compares the output of the register files. And then if we, so actually this processor just to support the BQ. Okay, so so we can use this very simple hardware that compares the two values. Okay, so I said how can, so in the previous class I explained how to detect some different bits in the two data. So we can use the exclusive OR. So because we can use this very simple hardware, then we can just add this special hardware in the after the register file, and then we can make the condition of the branch resolved earlier. Okay. So in the previous design, so it's a normal design. So if the branch is true, then this processor wastes 3 cycles, 3 clock cycles. But with the enhanced design, then this processor just wastes 1 clock cycle. Okay, understand? So for the normal processor, that means this processor does not have any special hardware that compares the two values from the register file. So we can draw clock cycle diagram like this. So we can figure out how many cycles are wasted by taken branch. So if the condition of the branch instruction is true, so I said it's a true, then it is called the taken branch. Okay, it's a taken. So we frequently use the word taken for the branch instruction. That means that the condition of the branch instruction is true. And then, so the opposite case, so false. If the condition of the branch instruction is false, we use this branch is the not taken branch. Okay, not taken. So we frequently use the T or NT for the result of a branch instruction. Okay, so like this clock cycle diagram, we can also draw the clock cycle diagram of this enhanced pipeline processor. So we can know that only 1 cycle is wasted by taken branches. Okay, that's what we learned in the previous class. And then before starting today's class, I will briefly explain about the lab number 3. So I will post the lab number 3 the Blackboard today after this class. And then people during today's class, before today's class, I will briefly explain the lab number 3. Okay, I will show the. So can you see my it's a Visual Studio Code? Can you see my Visual Studio Code window? Okay, good. Okay, so actually the goal of the lab number 3 is to design single cycle processor. That means the RISC-V single cycle processor. But in the lab assignment number 2, you were requested to design data path elements, but these data path elements need to support additional branch instructions like BNE, BLT, and BGE. So our single cycle processor also need to support these branch instructions, including the instructions that was explained in the textbook. Okay, that are explained in the textbook. So, so actually for this lab assignment number 3, I provide the completed design for data path elements. Okay, so if you see the lab codes, that you can find the completed data path elements. So if you fail to design the correct data path element in the lab number 2, then you can check your design with this golden design of the data path element. So let's see the instruction memory. So this is the code of the instruction memory. So some students asked about this FF. So actually you don't need to use this FF. So the designers, normal RTL designer frequently use this FF after the for the output of the D flip-flop, because actually the output of the D flip-flop changes at the rising edge of the clock. So that means that in the real design, so D flip-flop has also delay. So actually the output is resolved slightly after the rising edge of the clock signal. So we can use this delay to represent the delay of the D flip-flop, but you don't need to use it. So, okay. So this is the comment for this FF, the flip-flop delay for just better waveform view. So you don't need to use. Okay, this is the instruction memory code, and then actually in the lab number 2, you don't need to initialize the data inside of this instruction memory. But for this lab number 3, so you need to verify your design with the real RISC-V instructions. Okay, so that means that the instructions should be stored in the instruction memory. And then for this purpose, I already provide some RISC-V instructions that can be used for verification. Okay, so this is the binary code of the RISC-V instructions stored in the instruction memory. Okay, so there are total 17 instructions here. And then if you see that this instruction memory code, that you can find that, oh, this is some special code. So actually in the system Verilog, if you use this pragma, like the synthesis translate of, then this code is not translated for synthesis. So synthesis means that your RTL code is translated into some RTL code that use the basic gate. Okay, so actually your system Verilog code represent the behavior of your design. So it's not actual design, but in order to build the real digital design, your behavior design should be translated into the some synthesized design that use only the basic gate. Okay, but if you use this programmer, then this part is not translated for synthesis. Okay, so like a synthesis translate off, and then after that you can use the synthesis translate on. So if you see this code, then so initially this code is executed, and then this code fill the this array. This where is the array? So here this is the array of the instruction memory. The array of instruction memory is filled with the imem.mem. So this code includes the RISC-V instructions. Okay, and then register file. Where's the register file? So register file. So this is the golden code of the register file for single cycle processor. So you can find that how the write operation is implemented in the register file here. Okay, let's see the view. So actually this sign output is included for this lab assignment, because we need to support actually this single cycle processor support additional branch instructions, right? BNE, PLT, and BGE. Okay, so this is the sign bit, and then data memory. Oh, where's the data? So this is the data memory. Okay, so if you see that this data memory, then you can also find that the data memory is initialized with the this initial data. Okay, so data path elements are already completed, so you can use this golden data path element for this single cycle processor design. And then also I provide the skeleton code for the single cycle CPU design. So if you see that this single underbar cycle underbar CPU.sv system value, so then you can find that some codes are already completed, and then you can fill the some incompleted part in this single cycle CPU design. So just find this comment, like complete the main control unit here, complete the ALU control unit here, then here. So also you need to complete this fill this line. Like so, please find the fill this or complete comment in this skeleton code, and then please complete this single cycle processor design. Okay, so I already provide the required wires for data path element. So these wires are required for connecting data path element. Okay, but so for this single cycle processor design, this processor need to support the additional branch instructions here. Okay, so actually in the textbook, the branch control signal is a single bit signal, but our processor needs to support the additional 3 branch instructions. And so I modified the branch control signals, and then this branch control signal has 4 bits control signal. Okay, 4 bits, and then each bit represents the BQ, the corresponding branch instruction like BQ, BNE, PLT, and BG. So if you see this command for the branch control signal, then I believe you can understand how to implement this branch control signal. So it's a little bit different from the the single-sided processor in textbook, in the textbook. Okay, so also you need to complete this part, and then so please find the field this, and then the incomplete part of this single-sided processor design. And then in order to use the data path element, then you need to instantiate the data path element modules. So I already provide the instantiation of the instruction memory like this. Okay, so and then I believe you can also complete the instantiation of the other data path elements. Okay, so here also for this lab assignment, I provide the completed test bench. So you don't need to modify this test bench. Okay, so this test. So if you see this single-cycle processor module, then you can find that this single-cycle processor module has only two inputs, like clock and reset signal. So in the test bench, this clock and reset signal are generated, and then it's connected to the this single-cycle CPU. Oh, this is not completed, so you need to instantiate the DUT. Okay, it's not completed. Sorry. So you need to complete only this part here. Instantiate DUT, design under test. And it's actually it's simple. So like the instantiation of this instruction memory, then you can also instantiate the single cycle CPU under this test bench. Okay. And then other parts are already completed. So if you are interested, please, if you are interested, you can analyze this test bench code. I think it's useful. Okay. And then if you simulate this test bench using model sim, and then after simulation, you can find that this file is generated, report.txt file. And then in this report.txt file, the content of register file and the content of data memories are stored. Okay, after simulation. So so actually these instructions are executed, and then as the result of the simulation, I set the register file, and then the data inside of memory is modified. So actually in the first class of the chapter 4, I explained that, I believe I also explained in the chapter 2. So the result of instruction by processor is that the change of state inside of the processor or inside of the computer system, and then the change of state means that the change of data inside of the register file, and then change of data inside of memory. So in order to check the correctness of your design, we will check the content data inside of a register file and data memory. So if you see that this test bench, then you can find that, this test bench just stores the data inside of a register file like this. So the data inside of data memory like this. So if these instructions are executed in instruction memory, then the data of register file and data memory will be changed. So, so we will check this report.txt file to check the correctness of your design. Okay. So you need to also submit this report.txt also with your modules, so system value modules. Okay. Okay, do you have any questions for this lab number 3? Nope. Okay, so if you have any issues or questions, post your questions on the Piazza. Okay, let's go back. Let's go back to the. Okay. Okay. So I will explain about the branch prediction. So in order to reduce the wasted cycles by data hazard, we use data folding. Okay, and then I explained that we cannot avoid control hazard. Okay, but we can also reduce wasted signals, wasted clock cycles. Sorry, so we can reduce wasted clock cycles by prediction. Okay, so when I explain about the control hazard, so I explained that the issues in this control hazard is that is the condition of the branch where it's a result branch is reserved late. Okay, so that means if this condition of a branch is true, that means that this result of the branch is reserved, then we need to update the PC with the target bit of the branch instruction. So in this case, the clock cycles are wasted. Okay, so we need to focus on the reserved late. Okay, so then how can we reduce the wasted clock cycles? It's simple. If we know the result of branch instruction earlier, then we can reduce wasted clock cycles by control hazard. Why? Well, we don't know. We cannot know. So in this case, we can predict. Okay, so if we can predict the result of the branch with high probability, then we can make this processor works based on the result of predicted branch instruction. So the predicted result of the branch instruction, and then so we can predict the result of a branch instruction early because it's actually the actual result is reserved late, but we can predict the result of the branch instruction earlier. Then we can reduce the wasted cycles by control hazard from branch instructions. Okay, so this is called the branch prediction. So if you remember the 8 great ideas in computer architecture, so we learned in chapter 1, then you can find that the performance improvement by prediction. Okay, so this is the idea of prediction. Okay, but I explained that if we can predict the result of a branch, so anyone can predict the result of some instructions, Okay, like add x1, x2, x3. So actually we can predict the result of this add instruction for this x1, but the prediction, so that means that the hit rate, so hit means that our prediction is correct. So hit means that, but the hit rate is very, very low. So if this hit rate is very low, then we cannot apply predictions. But for the branch instruction, we can predict the result of a branch instruction with very high probability. Understand? So think like this. For I equal 0, I is less than 100, I plus plus. So if we see this iterative loop, then we can know that, oh, if we see this code, oh, we can know that, oh, this loop will be executed 100 times. So if this loop is translated into assembly code, we can find that some this statement inside of the iterative loop is translated into some assembly code from here, right here. And then you can find the branch instruction at the end of this code. And then the target of the branch instruction becomes the first instruction of this statement, T1. Okay. So if you see this, so if we see this code, we can know that, oh, this code will repeat this statement 100 times. So this is translating the assembly code, and the branch instruction is here. So we can know this branch will be taken how many times? So it goes back to the T1. How many times? 99 times. And then finally, not taken 1 time. Okay. So if we see this code, we can know the result of the branch instruction. Also, if we see the result of the branch instruction sequentially, then we can know that there's a taken, and then taken 199 times, and then not taken. Okay. So what can we observe? For this type of the branch instruction, if the branch instruction is taken, then we can predict that the next result of this same branch instruction can be taken with high probability. Okay, so there are different kinds of the branch instruction. That's true, but we frequently use this iterative loop in our high-level code, and that's right. If you generate some code, then you frequently use this iterative loop. Okay, then we can reduce the code length. Okay, so for this kind of a branch instruction, if the form the form of branch result is taken, then the future result, very next result of the branch instruction can be true with a high probability. So instead of waiting until the condition of the branch instruction is reserved, then we can predict the result of the branch instruction earlier. So by doing this, we can reduce number of wasted cycles in our processor design. This technique is called branch prediction. Okay. So with the branch prediction, we can predict the condition of the branch, and then based on this predicted condition, we can also control the pipeline processor. Then how can we how can we predict the result of the branch instruction? So for example, we can just check the formal result of the branch instruction, like true, taken. Oh, then we can expect that, we can predict that the next result of the branch instruction can be taken. Okay, so this is the prediction technique. If we monitor the previous event of the same instruction, okay, we need to monitor the previous events, the previous result of the branch instruction, and then based on this history, the result history, then we can predict the future event of the branch instruction. This is the basic prediction technology applied to our processor design. So for this prediction, we can track. So track means that we can just check one previous event or two previous events or three consecutive previous events. Okay, so if we just check the one previous event, then we can check the result of the branch instruction only for this one time. Okay, so that means that if the previous result is true, then we can predict that the next result can be true. And then it's not true, then we can also predict that the result of the next branch instruction is not taken, isn't it? Taken or not taken. Or we can also check the two previous events. Okay, like it's the taken, it's the taken. It's and then the result of the predicted branch can be changed by some algorithm or some baseline algorithm. So I will explain about this 2-bit predictor. So for example, if taken, it's a taken, not taken, not taken, not taken, not taken, it's a not taken, but it depends on the history of the previous event. Okay. So for this prediction, we need to check the previous result of the branch instruction. So we need to check previous result. So that means that we need to store previous result of a certain branch instruction. Like, so this is the BQ, blah, 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 and the BNE, blah, 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 BLT is blah, 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 blah. So, but in the code, there can be many branch instructions. So it's true, right? So in our code, there can be many branch instructions. So we just store the previous event of each branch instruction. So we just store it's taken, the previous event is taken for the BQ, and then not taken, so previous event of the BNE, and then taken for the BLT. So this is just branch prediction. For branch prediction, we need to store the some previous events, like, so it's a T, it's a taken, not taken, it's a taken. This is the BQ, BNE, or BLT. Okay, we need to store the result of the previous result of each branch instruction. So how can we identify this branch instruction, like How? So how can we identify different instructions in our processor? Can use program counter. Okay. Right. Different instructions have different program counter value. Okay. So in order to distinguish, so in order to identify different branch instructions, we can use the PC of the branch instructions. Okay. So for example, if a PC is the 04 for this BQ, and then the 12 is the 22, then we can access the previous result of the branch instruction with the PC value of the branch instruction. But we cannot use entire PC value. We can just use the part of the PC. Okay. So for this dynamic branch prediction, it's a branch prediction. So we need the branch prediction buffer like this. So the previous result of branch instruction is stored in this branch prediction buffer. Okay, the first. And then this branch prediction buffer is indexed by branch instruction address, that is the PC of branch. Okay, program counter of branch instructions. Okay, so based on the PC, like 222, this result of branch instruction is stored. So let's see the example. Oh, slow. So it's a BQ is here, then some instruction is here, and then the PC of this BQ is, let us say that the PC is about the 1, 2. So this is the branch prediction buffer. So with this PC value, the history of this branch instruction is stored. So if this branch is taken, like T, then we just store the T, so that is taken, indexed by PC of the branch instructions. Okay. And then if this real result is the T, and then also this branch is taken, then it's also T is stored. And then it's not taken, then N is stored. Okay. So let's start from this. So this branch instruction is executed, and then let us assume that the result of the branch instruction is true. Okay, and then it goes back to the first instruction of this iterative loop, and then it's executed. And then this branch instruction is fetched from the instruction memory, in the instruction fetch memory with the PC 12. Then we can access this branch prediction buffer with the PC of the branch is the 1, 2. Then we can know that, oh, the previous event for this branch instruction is true. Then we can predict that, oh, this is the instruction fetch stage. So we don't know the real result of the branch instruction, but based on this branch prediction buffer, we can know the previous result of this branch instruction. And then if it's a taken, then we can predict that, oh, the result of this branch instruction can be taken. Okay, so that's how we can predict the result of a branch instruction earlier. Okay, do you understand? Yeah, so this is the a little bit tricky part, because you are learning the prediction technology for the first time. Okay, so this is the prediction technology in the processor architecture, but I believe you are learning about the prediction technology for the first time. But this technique is frequently used also in our real life. Okay, we predict the result of our future event based on our previous result. So actually everyone predicts based on the history, and then the same technique can be applied to our processor design. Okay. So this is the 1-bit prediction. So this is called the 1-bit prediction, because we can only check the one previous event of the branch instruction, and then the taken or not taken can be represented with 1-bit data, because it's just taken or not taken, just two cases, so 1 or 0. So we can use 1-bit for this taken or not taken case. So that's why this prediction is called the 1-bit predictor. 1-bit predictor. And then I said that we can use two previous events of the branch instruction. So that means that we can use 2-bit branch predictor. So 2-bit predictor means that for this branch prediction, we can just monitor two previous results of the certain branch instructions. So let's see this case. So this code has the two iterative loops, so like inner loop and the outer loop. So for example, it's like this case: for I equals 0, I is 100, I plus plus, and then actually the nested loop, j equals 0, j is less than 100, j plus plus. So this is the two iterative loop, and then this is the inner loop, and then this is the outer loop. What's the problem of the 1-bit predictor? The prediction can be false for this inner loop. Okay. Why? If we just see the result of this inner loop, like this loop, then we can know that also the event of this loop is the true taken, and not taken. So 100th event, and then based by this outer loop, this is go back to the first instruction of this outer loop, and then the inner loop is also executed again by this outer loop. So what's the real event for this inner loop? Like taken. But it's the real event, but it's a real. With the 1-bit prediction, 1-bit predictor, we can predict the result of this inner loop as what is the result of this? What is the prediction of this loop for this iteration? It's taken. So taken. Oh, this is prediction is missed. The prediction is missed. So that means the prediction is incorrect. And then also this is NT, because the previous result is not taken. but this is also long. Then taken, and then the same pattern is repeated. So if we just use the one-bit prediction, then for this case, then this branch is mispredicted twice at the end of the inner loop. Like once here, first here, and then the second here. Okay. So in order to avoid this case, we can use the 2-bit predictor. So 2-bit predictor is just monitors the 2 consecutive previous events of the branch instruction, like 2 consecutive events. And then based on this event, then the predicted result is determined. Okay. So the 2-bit predictor is just similar to the saturated counter. So this is the some state diagram. So this is the taken, and then this is the NT. No, this is the 1 1, and then this is the 1 0, and then 0 1 and 0 0. So from the current state, then based on the result of the branch instruction, the state is changed. So let us assume that the current state is 0 0. Okay, and then if the result of the branch instruction is taken, then the state is changed to the 0 1. Okay, but so the branch is taken, so the state is changed. But if for this state, the branch is predicted as not taken. So what is different? With the 1-bit predictor, we predict that the branch will be, the result of the branch is identical to the previous result of the branch instruction. But with the 2-bit predictor, the prediction is based on the state of this branch predictor. Okay. And then if the branch is taken again, the state is changed to the 1 0, and then in this case, the branch is predicted as taken. Then so it's also a taken, not taken, not taken. So 2-bit predictor is a little bit different. So we just check the 2 consecutive previous result of the branch instruction, but based on this previous result, the state is just changed. The states are changed like a saturated 2-bit counter. So and then based on the state, then the result of current branch instruction is predicted. Okay, so this is the 2-bit predictor. So if we use this 2-bit predictor, then for this case, it is predicted as the taken, and then taken. So it is correct, but we cannot avoid this case. Okay, understand? So this is the branch prediction. So actually, the branch prediction is very critical for the performance of our processor. So you may think that a branch instruction is very rare, but actually in our code, the branch instructions are frequently used, and then that means that the branch. So when because of the frequently used branch instruction, that means the control hazard happen frequently. Then control hazard happen frequently, then the performance, the clock cycles are wasted. That means the performance is degraded. So actually the branch prediction is also critical for the performance of a processor. Okay, this is a very good idea. So that's why the prediction is the great idea for computer architecture. So we can improve the performance of computer processor with good branch predictor. Okay. So this is, so I explained about the branch prediction, but what's the another problem is that target of the branch instruction. So when I explain about the branch prediction, then I explained that the history of the branch instruction is stored in the branch prediction buffer, BPB, and then this branch prediction buffer is indexed by PC of the current branch instruction. So that means that, so this current PC is determined at instruction fetch stage, right? So in instruction fetch stage, we can know the PC of the branch instruction. That means that we can predict the result of branch instruction at instruction fetch stage. So that means the BQ is, the PC of the BQ is 1, 2, and then we can just access the branch prediction buffer with this PC value, and then we can read the previous result T. Then we can predict the result of this current branch instruction as taken. So we can predict the result earlier, very early at instruction fetch stage. What's the problem? The branch instruction is composed of it's the result of the branch, the condition of the branch, it's a condition, and target. Okay, the branch instruction is composed of condition and target. We can predict this condition, the result of a branch instruction with branch prediction buffer, right? Which stage? Instruction fetch stage. But we don't know the target. Where is the target of the branch instruction? Where is the target? Actually, the target of the branch instruction for RISC-V is the current PC, the PC of the branch instruction plus immediate value multiplied by 2. And then where is this immediate value? Oh, immediate value is in instruction. What's the problem? Actually, we can know the target of the branch instruction at ID stage. It's the target. Okay. So we can predict the result of the branch instruction at instruction fetch stage, but the target is reserved at instruction decoder stage. So even though we use the branch predictor, the target is reserved in ID stage. So one cycle is still wasted. Okay. So understand? So in order to avoid this case, we can also predict target of branch instruction. So I use the word predict, but it's not actually predict. Why? If you see the branch instruction, this is the assorted branch instruction. The branch instruction has program counter value, and then the target is included in the instruction as an immediate value. So actually, we know the target of the branch instruction when this branch instruction is executed once. Understand? The target of a branch instruction is a PC plus immediate value multiplied by 2. And then actually immediate value does not change, right? PC is the identical value for this branch instruction. So target is also constant for a certain branch instruction. Do you understand? What does that mean? If we just store the target of the branch instructions, then we can reuse this target. We can store the target of the branch like branch prediction buffer, like this, indexed by PC of the branch. Okay, then the target is stored in the branch target buffer. Okay, so in the instruction fetch stage with the PC of the branch, we also access the branch target buffer with the PC of the branch instruction. Then we can get the target of the branch instruction. So at the instruction fetch stage, we can predict the result of the branch instruction. We can know the target of the branch instruction. So in this case, based on the prediction result, the next instruction can be fetched immediately for next cycle. Do you understand? So when the branch instruction is instruction fetch stage, we can predict the result, and then we know the target. We can predict the result of a branch using branch prediction buffer, and then we can know the target of the branch instruction with branch target buffer. So if we know, so let us assume that we know the result and target of the branch instruction, then we can just jump to the target of the branch instruction if the branch condition is predicted as taken. Okay, so any cycles are wasted. If the prediction is true, that means the prediction is true. And if we already know the target of the branch instruction, then cycles are not wasted. Okay. So using this prediction technology, we can reduce. I said reduce, we cannot avoid, we cannot remove totally. We cannot remove the all wasted cycles, but we can reduce wasted cycles by branch instructions. Understand? So this is the prediction technology. So actually the prediction rate cannot be 100%. So it's not perfect, but with the high probability, we can predict the result of the branch instruction. Actually, the researchers invented many good predictors. So I believe that the prediction rate, the hit rate of this branch predictor is around it's higher. I believe it's higher than 95%. Okay, so the branch is very predictable, and then based on this characteristics of the branch instruction, we can use branch prediction and branch target buffer to reduce control hazard. Okay. So I believe this topic is a little bit tricky because as I mentioned, this is the I believe you are learning the first prediction technology in the process of design. So, but it's very critical for the performance of a computer processor. So it's very important technology. Okay, and then this prediction technologies are widely applied to actually many aspects of the computer process architecture. Actually, various types of prediction technologies are applied to real computer processor architecture. Okay. And except, so I briefly explain about the exception, but I believe I cannot complete the exception part. So I will complete this pipeline design part in the next class. So I will briefly explain about the exceptions. So until here, we learned about the pipeline architecture and how to build the basic pipeline architecture and control signals. And then we learned how to handle hazards like data hazard and control hazard. So these are required for handling normal instructions or normal behavior of our code. But our processor also need to support exceptions. So what is exception? What is an exception? So in Korean, that is called the 예외. Sometimes it's called the 예외, but exception means that it's a rare event that can happen in computer systems. So the meaning of the exception is the unexpected event. So for example, divide by 0. We cannot compute the divided by 0 because it's not defined, and it's same to the computer processor. If the assorted number is divided by 0, this computer processor cannot generate real number. So this result is not defined. So then, if this result is this event happens in the computer processor, then we need to, actually the computer processor needs to handle this rare event. So this unexpected event. And then in order to handle this unexpected event, the computer processor needs to support exceptions. Okay. So I believe someone have heard about interrupt. So in the computer systems, so interrupt means that the interrupt is caused by I/O devices such as mice, keyboard, or touch screen. So compared to the normal instructions executed in the computer processor, this typing or mouse click or some touch screen touch is a very rare event. Okay, so sometimes the processor need to handle this rare event by users, like from I/O devices, and then also this, in order to handle this interrupt, then the computer processor also handles this interrupt like exceptions. So sometimes the exception, the interrupt is not an unexpected event, but it's rare event. But so interrupts are also handled like exceptions. Okay, so this is the meaning of the exception and interrupt. And then in the next class, we will learn how these exceptions and interrupts are handled by pipeline processor. Okay. So so actually, so as I explained, as I mentioned, the basic scheme of pipelining architecture is very, very simple. So I believe everyone can understand. But these corner cases are, it's a little bit tricky. Okay, so but it's also true for our real world. So actually, basic concepts are very simple, but it's not easy to handle exceptional cases or corner cases. Okay, so in the next class, I will explain about how to handle exceptions in the pipeline processor. Okay, and then I will post the third lab assignment on the Blackboard today. And then and then I will conclude the chapter 4 in the next class. Okay. Okay. Do you have any questions? It's a very good question. So BPV is addressed with PC. Then, so the PC, the width of the PC is very long. So that means that the number of entries in BPV can be also very large. So in order to avoid this case, so we just use the part of PC. Okay. So that means that, so we can say that our PC is a 64-bit, but we cannot use entire bits of this PC. Then for this branch prediction buffer, we can use only the part of the PC, like 16-bit or even the 12-bit of the PC of this branch instruction. Also, for the RISC-V, there is the PC +4. So actually, we can drop the LSB 2 bits for the instruction. Okay, so I mean we just use the part of PC address of branch instruction for BPB or BTB. Okay, it's a very good question. Okay, thank you for your attention and see you in the next class. Bye, guys.